Thank you, Matt, and Bruce, and Matters, and all the organizers. And 3 years, fantastic jobs you have done, actually. Today, I also have another separation. I have 3 months separation. I have been in this group for 3 months. Yeah, I actually inspired by this group. I started the Kaggling this January. This is my first talk. And actually, I'm looking for a job. If you want to, you look someone to identify well, yeah, do message me. And if you want to understand what well is speaking, what their language, also send me a message. Okay, now let's start it. So the name of the competition is Humpback Whale Identification. Yeah, here you go. I'll start with the overview of the competition, then give some explanation of the data and what challenges we have faced. And after that, I show the procedure, the pipelines to identify whale, and what are options we have, what are the state of techniques we can follow. So after that, I'll show my solution and also winner's solution. You can see why they are winner. And at the end, I'll share my experience from this competition. So this competition is, here we go. Yeah, this is a logo of the Happy Whale. They sponsored this competition. And you can log into this website to see they have, so far in their database, there are 150,000 photos and a lot of reports about in counting. So if you have you have photo of whales, you can submit your photos to this website. They will identify if your whale is in the system. If not, they will give an ID later on. So actually, this website, there are a lot of information. I think if you want to find out where to see a whale, that's the place. I input the British Columbia, and it pops out a lot of places you can look for. If you put your mouse on this dot or this square, it will pop out the time and the place, location. Then you can just at that time go there, and you will get pretty good chance to see a whale. So, what's the motivation of this competition? Basically, the ultimate goal is to help them to conserve whale population because of climate change and also overfishing. So these whales, they indeed have a hard time. So actually, scientists have established a photo surveillance system. They try to keep track individual whales and identify them by their shapes, or no, by their tails or some unique markings in the photo. And trust me, actually this work is very tough, especially when you do this manually. When later on you can see some picture, it's not an easy task, especially if you do it manually. So fortunately, thanks to the breakthrough of computer vision, nowadays we can do this, computer can do all these things for you. And the competition, in this competition, will be provided with 25,000 images. And some of these, yes?
I was just wondering whether all of the images in this competition were photos of the whale's tails, or whether the other parts of the bodies were also included in the analysis.
I think most of the whales are their tails.
Okay, thanks.
Yeah, but the tails sometimes maybe just one tip, just small tip, but sometimes you will get a whole span of the tails. Yeah, and also different pose, right? You can, because photo, whales, they did not supposed to make pose for you to photo, right? So, that's a challenge of this competition. So, by analyze these images, we are supposed to build an algorithm to identify these whales. Yeah.
I just have a general humpback whale question.
Sure.
Do you know how many humpback whales there are in the world?
I don't know. In this competition, there are 5,000.
Okay. If you go back one slide.
Sure. Where's the? Oh, up here. Okay.
Oh, one more slide. What does it mean, 21,000 individuals here?
Individual probably means contributors.
Oh, okay. Contributors.
Yeah. If you have a picture, you can become a contributor. Just submit the picture into the system. This competition ended on February 28th. There were 2,130 teams taking part in this competition. Actually, this competition has begun like 8 months ago. Yeah, initially it's at the playground. And later on, Happy Whale decided to take this challenge seriously. Then they upgrade to a competition. So they give out prizes for the top 5 teams. At the playground, actually, the top score is about 0.78. And in the competition, during a short time period, the score boosted to 0.97. That's huge. Actually, amazing. Well, this is all obviously also based on the findings at the playground.
I'm just going to fill in, if anybody was wondering about the humpback whale question, Dan's pulled up a wiki page. It says the worldwide population is at least 80,000. And then it has some information about where the 80,000 are, and it says down from a pre-whaling population of 125,000. So they're still doing okay, I guess.
All right. Actually, if you want to get first-hand or hands-on experience on computer vision, I highly recommend this competition. Why? Because first, this competition covers almost everything. Image classification, image segmentation, and feature extraction, and a lot of things, and so on. And also, you can you can design different loss functions and play around with different loss functions, and a lot of things in this. And you can also put a gain in your model. So if you are too overwhelmed by if you think, oh, that's too many, well, you can just focus on one aspect. And another amazing thing about this competition is all the top players, the teams, they publish their solutions in very detail. Their experiments and how they get to their final score. Each experiment does it work or what kind of improvement does it give? Very detailed. And to make things better, these top teams, they also, almost all, they publish their code. So if you want to get first-hand experience, you just learn their code, then you can go through all these details. Let me repeat my words. I highly recommend this competition. So start with computation, we always first look at the data. So you can download the data from this link, and this link will give you a whole training set of the images, and also the labels for the whales in the image. And the labels, some they do have IDs, some they don't have, because before they do this manually, they cannot ID all the whales. So there's a lot of whale is unID'd. So, and also in the data set also will provide the test images. And the task of this is you build up algorithm, make a prediction, and submit your file. For each of these images, you give 5 predictions, and put the first one you think you most are confident, and secondly confident. And you see new whale here. Well, if you think you are not confident with available IDs, you might put a new whale in some place. And the most important thing is, keep in mind the order matters, the order of your predictions. Why? Let's look at the score. How they evaluate your prediction. They use.
Sorry, can I ask a question?
Yes, sure.
I didn't quite understand the new whale.
Oh, new whale. New whale means in their training data set, if there's no ID, they just label it as new whale. If they have ID, they just put ID.
Okay. So there could be a whole bunch of whales.
Exactly. That's also a unique of this competition. So the prediction is evaluated by map 5 at 5. What this means, if you look at this, actually this equation, at least is not very straightforward to me. And let me try to explain a little bit about this formula. In this equation, we do average, right? So we have the number of images. Then for each image, you calculate the cutoff precision, cutoff at cutoff k, that's the pk, and the relevance. This is an indicator. If your prediction got a hit, then this is 1. The value of this gives 1. If not match, then it gives 0. So n is the number of prediction. Actually, well, this means we all predict 5. So this is just 5. So question? No. So, and in this formula, once well, we start from K, the K starts from 1 to 5. Actually, once you find some match, if you find your match at the second place, your second place prediction is same as the label they give. Then you just stop this. You don't need to go up to 5. You just stop at 2. So, confused? Yes, me too. So, yeah. So I think let's speak in English. Maybe it's easier for us to understand. Basically, I want precision. Well, I think most people knows what precision means. So it's defined as the number of the correct prediction, true positive, divided by the number of true positive plus false negative. What means true positive? For example, we make some prediction. I give we have 10 whales. I give some ID like 007, all the whales. Then we make some prediction. If that whale ID is 007, you got true positive, one true positive. So if you don't, then it's false positive. So that's the precision. Now, what's the cutoff of precision? Precision at the cutoff K. K means you choose rank 1 through K. For example, if you predict the first your prediction is correct. This clause means correct prediction, and the others are just incorrect. So if you predict correct at the first place, the P1 will be 1, right? Because you only look at 1. Your true positive is 1, and the false positive is 0. So you get 1. So that if you you will get MAP at 1. You don't have to go to K equal 2, 3, right? You already got hit. You got matched. Then if your prediction at second place is correct, then P1 will be 0 because P1 you only look at this prediction, right? It is not correct. So true positive is 0. So then you get 0, right? But if you look at P2, we only look at these 2 predictions. First, you have how many true positives you have? 1, right? You have 1. Actually, it's always 1 true positive. And false positive is 1. So you will get 1 over 2. And if your prediction at the third place is correct, then, at the P1, P2, they all are 0. Only at P3, you look at all these 3 sets, you have 1 true positive and you have 2 false positive. Then you will get 1/3. Well, to make things easier, let's say your prediction, if you hit first prediction is correct, you will get this precision at K is 1. If you at second place is correct, is the precision is 1 over 2, and so on and so forth. Actually, if speak in this way, I think it's more easier to understand than look at the formula itself. So that's the evaluation. Okay, let's look at some figures of the whale tail. I put here, well, these two column gives the the whale tails, they have same ID. For example, these two whales, suppose they should be close. They should be the same. But for me, this is different ID. For me, I look like these two are quite similar. These two are, they are not so obvious to me. They are the same. So that's, actually, if you look at these two also, right? And actually, to me, if I do this manually, I don't know I can, take the difference, tell the difference. So let's look at the EDA, explanation of the explanatory data analysis. Actually, when we, as a data scientist, we are always talk about we should do this before. Yeah, go ahead.
I have a question. How did you have a local validation score? Because it's like you don't have like a list of predicted values to calculate your precision. How did you do it locally, or were you using a leaderboard? Do you have a local?
Yeah, good question. Suppose should some validation data set. I do it on Leaderboard, based on Leaderboard. Actually, not really. I look at also my training curve. If my loss function, I also look at training the accuracy of my training. If the accuracy not increasing anymore, then I just stop. It's not a good way. Good way should always set up some validation data set. But most people in this competition, because we don't have enough data. There's one group, they did this, they pick up some validation data set. How to design, actually you need to very carefully design your validation data set, right? Because your ID, there's limited ID well. And you want to keep this ID well in your training data set. If you put it in a validation data set, because this ID, you need these IDs, right? Because your testing data, you will give some idea of the testing data. If you, lot of the ID will only have one image. So if you put it in validation data set, it doesn't make sense, right? Actually, there's one team, they did this, they pick up some IDs, they have a lot of the images. Then they can pick some, from that group, they pick up some as validation data. But most people, they don't do I don't say they do validation in this computation. All right. Yeah.
I wanted to ask about the whales that have 1 and 2 and 3 images. Like if they just have one,
Right.
that they would just have the label new whale. Is that correct?
No, if they have one means they have ID. It's
Okay.
There's ID. There's a specific new whale, they don't have ID.
Okay. So is there ever a case where the same whale would be in a data set with both the labels new whale and an ID, like that they're supposed to recognize this is a new whale the first time it encounters it and then assign it an ID
You mean different?
later for validation or for testing time?
Well, probably that would be noise because you see, you give label to this training data set. Well, most this work has done by people, like absolutely it's possible they make a wrong label, but actually that can be some of noise. It's quite normal. Well, when you train a neural network, there's some voice in your data set. Well, some neural network is quite robust to noise. Also, actually, if you want to get a good performance, sometimes you need input some noise in when you're training these things. Yeah.
I was just wondering whether anyone attempted to do any data augmentation in order to increase the number of examples they had per whale.
Yeah, that's good. Yeah, that's a good question, and actually, very heavily augmentation needed. So this figure shows actually every time I know. Well, I was told that we should do EDA before we do any modeling, right? So yeah, well, I realized this after the competition. After I look at the winner solution, and I say, oh yeah, I should. There are a lot of time, I should, moments in this competition. For me, I mean, I'm quite new. I started Kaggle in this January. So actually, there's a lot of information in these figures, and it's quite useful when you choose your training data set and also how to design your algorithm. And from this figure, you can see this figure, the x-axis is the image count. There are 2,000 whales have just one image. So that's the reason it's not. We cannot put this into the validation data set, right? Absolutely, we cannot. If we put it in validation data set, then if we do a validation whale, this whale will be ID'd as new whale because in your training data set, there's no such whale, right? So, and 30% whales, they have 4 or less images. And there's a bunch of new whales in this data set. New whales means they don't have any ID. But still, there are some whales, they have a lot of images. The question is, how do we make good use of these figures? Well, later on in the winner solution, someone actually makes very good use of this message. And another thing is about the image resolution. Actually, there are 7,000 unique resolutions. I mean, how many figures we have? We have 25,000, right? So, I mean, most resolution they are different. So, but fortunately, you can see most popular covers almost half of your data set. So, as I said, it's not easy to identify these whales because we have 25,000 images for 5,000 whales. For 3,000 whales, only have very few examples, and a lot of whales they don't even have ID. So also resolution is different, and also the pose of the whale. Well, see these two pictures. One, you can see the full fins, the two fins. Another one is too short. You can only see only one fin. So also the weather also illuminating and also age of the whale can make this identification difficult. Yes.
Was there any consideration of the whales, the physical features? For instance, like 40% of the whales just have one image. So what if the picture was taken on the other side of the flip?
Oh, physical, you mean?
I mean, the physical feature. Does
it's
one side
touch-like?
of the tail resemble the same way with the features from the other side as well?
You mean background or physical or?
I mean, for instance,
how the texture of the
yeah, the texture.
texture. Actually, it's only images, right? I don't. Yeah, we don't touch them. But sorry, I didn't get your question.
Now, what I'm asking is like, based on the data, 40% of the image, 40% of the whales just have one image.
Right.
So, what if the other side of the tail, like images just have one side of the tail, right?
Right.
If it is on this axis, then you don't see either side of it.
Right.
If it has it, then it is just one side. So there is a presumption that each image is of a different whale. What if half of it is from the other side of the tail? You don't know if it is of the same whale, right?
Each, you mean, actually, some ID have several images. Some have only one. Some don't have. You mean the new whale, they have some, in the new whale group, you may have same whale. That's possible because those data are untagged. So it's possible in your new whale, in new whale group, you have same ID. You have same. They are not ID. You have same whale.
Same whale with two IDs, two different IDs.
No, they are not. Oh, I mean, I think quite close to the question he just asked. But in the new whale, it's yeah, of course it because all this new whale group, those pictures are untagged.
Yeah. Okay. So the IDs that you're talking about, they are data sets given by as a part of the competition. So they are not IDs that you're recognizing from the images.
These IDs are given by the training data set, coming with the training data set.
Yes. So you're not trying to identify if each whale image the whales in each image are unique or not. You're just taking that if the whale tail is there, it is an instance.
Yeah, absolutely no. We need to do is for the testing data set, you give it an ID. If it is in your data set, in the training data set, then you give it the exact ID you predict. If not, then you put a new whale in there.
Okay.
Okay, I think I want to try my bet at trying to understand what's going on here. So, from what I understand, there's this new whale category that's maybe causing a little bit of confusion. So in the new whale category, there's probably a bunch of the same whale that has appeared in that new whale category, but it has not been ID'd. And so there's probably duplicates of certain whales in your testing set that belong to one of those whales that you've seen before in your new whale category.
Yes, exactly, yes.
In terms of the same ID, of two different IDs referring to the same whale, I do not think that that is the case. There's probably some error in the way that they've been labeling, so maybe that's happened, but I think that they've tried to avoid that from happening. You guys were talking about some stuff about this. Is there anything, did you guys have any other thoughts?
We were just talking about that you would get photos from both sides, and potentially, if you're like in your boat going past the whale, then if you had photos from both sides, then you could label that whale as the same whale. Like you would know that because you literally just took that photo. So assuming that a significant number of them are done like that, then that would be convenient.
Yeah. Thank you for answering question for me. So, and to do this, to solve this problem, usually we start from within our approach image classification. Actually, this is well, for image classification approach, it's not easy at all. And because limited examples of each class. So normally people choose, well, they define this, we call this as a low shot identification problem, like a face recognition. In our case now it's tail recognition. Yeah, so, well, I didn't mean, well, classification cannot solve this problem. Actually, there's one group. They use classification and their solution, their score is at 7th place. Actually, it's very amazing. They did fantastic work on that. So, but most teams, they use the techniques from face recognition to solve this problem. And what we all know face recognition, and what's the history of that? I go faster, I mean, since we have a lot of slides. And for this figure shows the history of the face recognition. And there's one point I want to make is, from this figure, actually in 2014, this is, I think it's a milestone of the face recognition, because at this year, these two approach, these two deep face and deep ID, they match humans' performance. For example, the accuracy reached 97.5. So, and even today, these two, two methods have been widely used. After that, a lot of researchers have pushed this accuracy to 99.5 and 99.56. They are not stopping, and I don't know, maybe they try to make it 100. So basically, the pipeline to identify whale, first we start with the pre-processing. What we do in this processing, we actually, from whales, you can put some landmarks on this whale and generate a binding box. Then we only take this part as the input. Why we do this? Because now the picture is much smaller, right? Then you can train much faster. You can train your neural network much faster because the input size is smaller. And also you include a lot of distraction of the background. So that's the pre-processing. And after that, as you mentioned, asked a lot of yeah.
I was just wondering how they went about doing that cropping, whether they designed a separate algorithm to
Yes.
do that boxing. Okay,
Yes,
yeah.
exactly. Yes. You see this link? This is the binding box model, the kernel. Most people use the results. I use the results from this kernel. And actually, I want to point out Martin. Actually, he's the top player in at the playground here. And a lot of his findings in that playground and his code have been widely used in this competition. And also, someone has pointed out, Martin, he is also the winner of famous Netflix competition. I think Netflix is maybe 3 years ago, the competition, the very famous Kaggle competition at that time. Because at that moment, I think they offer 1 million prize. That's the reason, yeah. And actually, Netflix did not adapt the top one solution. Yeah, because, well, accuracy, yeah, is very high. But because also when you do inference, efficiency also is what you need to consider. I think that's the reason why that competition is famous. So the face recognition, after processing, there are several parts for this recognition. First thing we need to do is the augmentation. There's two types. It's one-to-many. What mean one-to-many? Well, you have one figure. Actually, we have a lot of figures only have one shot. So you need augmentation to generate a lot of copy of this, but you cannot be exact same. So you do augmentation. Augmentation, you can use some data augmentation. You can use a lot of augmentation techniques can use. And another augmentation is many-to-one. This is if you have for one ID where you have a lot of pictures, then you can do this many-to-one. So after you do this augmentation, you process this tails. Then you input this to your training neural network. You need train. You pick some CNN architecture. Then use this neural network generate features. Then these features will fed into the some loss function. You use this loss function. You can see, normally when you're training, you will input two figures, two images. One image, these two images, they might be the same, or they might have same ID, or they don't have same ID. If they have same ID, then the distance you calculate should be small enough, right? You should be very similar. Otherwise, if not similar, you will get a very large loss function. If they are different from different ID, then suppose the distance of these two features should far away from each other. If you get very small, then you will get a big loss function. Then the purpose of training is we minimize this loss function. Then we get weight of this some deep neural network. Then after training, the weights of neural network will pass to, well, these weights will be used when you do in the inference. Inference is you have some test, you have some image in your test data set, you put here and put it into the same neural network and get a feature of this testing image. Then compare, actually after training, you will get the features based on this, you will get the features of all ID'd whale. And your test data will give you one feature, right? Then this one feature compared to all the features you get from the training data set. I mean, all the ID'd whales in your training data set. Then you can use some like tail matching techniques. You can use machine learning also. Or you just calculate the distance. So if it's close enough, you just say, hey, these two have the same ID. So that's pretty much the procedure to do this identification. And this figure quite similar. Actually, if I didn't say it clear, you can look at this paper and this. Yes.
Yeah. To finish that thought, like the paper, but I just wanted to point out that there's going to be like maybe 15 to 20 minutes left. And I don't think you have a lot of slides to go.
Okay, I'll move faster and faster. Yeah, okay.
But definitely try to get to your solution and the winner's solution.
Okay, surely.
Yeah. And for everybody else, let's try to maybe save questions to the end, unless it's like a really good question.
So in augmentation, I already mentioned the augmentation, and in the design of the neural network, actually, this here shows two. You can use actually multiple networks. Actually, during computation, I don't know how to do that. After that, actually, the top one team, they use multiple network. They use like most team, they just treat one classification problem. They treat it two classification problem. And this component in this box lists some loss function you can choose from. And after training, then you go into the input testing. Input into your testing. Actually, there's no, and almost the same. You have the same network as in your training. And this slide has almost the same information as previous one. Also, I mentioned augmentation. What I did, I used some package and do the data augmentation. And now what deep neural network should we choose? Actually, this paper shows the benchmark of the popular deep neural network architectures. The size means the size of this dot is the size of the architecture. The criteria is we want the size of this as smaller as possible, right? Because you have less parameter, means you need you can rent in if you can use smaller memory size to run this model, but it's impossible. If you for this architecture, it's impossible to run in small computer, and also this axis shows the calculations involved. So basically, we also want to choose as left as possible. So the basic thing is usually we start from simple architecture. I choose the ResNet 18, and also I have tried another denselet. Actually, this you see this size of this dot is also quite small. And also, this figure shows not sure well which one you're familiar with. Also, start with whichever you're familiar with, and because training, if you're familiar with one, training maybe you will save a lot of time in training. So this figure shows the actually very popular ResNet. Like I think a lot of people know what's ResNet. ResNet. I just skip this. Go to next, and also squeeze and excite ResNet. And you can find information from this paper. And they also claimed that if you put a squeeze and excite before any of your neural network, you will get the good performance. The truth is, yeah, it's true, yes. So once we have this neural network, then we can get the features. For example, if you have two images, and you can get the features. Actually, I took this slide from the Coursera deep learning course. It's taught by Andrew NG. Yeah, this is a very good course if you want to learn deep learning. So then features, you have two features for the two images. Then next thing you are going to do is to calculate the distance of these two features. The distance means degree of difference. You can define according to different criteria, or maybe you can define what's the Euclidean distance or what's the angular distance. Yeah, a lot of things you can try out. So if the distance is small at some margin, you say, hey, these two, they are same person. If they are not, they are, if greater than some margin, you say they are different. So another thing I want to point is the triplet loss. And triplet loss actually is basically you pick an anchor. Well, this is, someone have ID, and you pick another, have same ID as the positive example, and you choose another as another with a different ID as a negative example. Then you use this formula to get the loss function. In your training, when you train a neural network, you want to make this loss function as small as possible. All this information you can find from this deep learning deep learning course. And this figure shows what loss function you can choose from. Lot of choice and a lot of math. I will not go detail into that. And this table shows what's the state of art of the face recognition. You can see nowadays the accuracy is already being 99.8. And there's a lot of choice you can choose, like arc face, cos face. Actually, all this paper, they also provide the code. So, well, if you want to try this, you can run their code and look at the details. And to see, here are some very useful kernels. To save some time, I think almost, it's always a good, it's always good to start from some baseline kernel. And from there, then you can make some changes. This slide shows my solution. Actually, my solution, the figure slide, I put the fig of my input, I make it to 384 by 384 and in 3 channels, RGB. I think this is this resolution. Well, if you can go to high resolution, absolutely you will get better performance, but also it takes a longer time to train. And I use a lot of augmentation tried, and I tried to spray some salt or pepper on the image because I saw, hey, there's some water bubbles around, but this turned out doesn't work. So also, the optimizer I use add-on, and I early stop. Early stop means when I found the accuracy of the training not increasing anymore, then I just stop there. Also, I use, as I said, I also use Leaderboard. If my score goes down, then I stop. I don't train anymore. I tried 2 models. First one is use DenseNet 121, and use the Triplet Loss and hard pairing. Another model is ResNet 18. Siamese, this loss function is binary cross entropy, and use this linear assignment problem solver to do the pairing. In this case, use hard pairing. In this use LAP. Actually, this is very essential. Well, in this model, I got score around 0.9. In this, I only got in private board is only 0.855. I think this is very essential when you do the pairing. Also, I tried test time augmentation. Actually, test time augmentation do augmentation on a test data set. It turned out not working. Later, actually, after computation, I look at the figure I just showed. Well, when you do testing, what kind of augmentation? They didn't mention the tested augmentation, so no wonder it didn't work out. So this is actually finally I trust my test time augmentation. This is my submission to the final submission of mine, and the score is in a private is 0.899, and the final rank is 183 out of 2,000 teams. And here's the leaderboard. You can see the leaderboard. The top one, the accuracy is 0.97. That's it's amazing. And all these 5 teams, they share their code and their results. If you want to look at, you can go to the discussion section. You will get all the information. Now I go through the winner solution. The first place, some highlights of this solution. This is a link of the discussion of their solution. And the overview, they use 2 classification. And the network they use is SNET 154. And input size is 5. This is their input resolution. Actually, see, this is not square. It's some rectangular, I think, according to the input data, the box, right? And the difference of this is Another difference is they use 4 channels. Normally we use 3 channels, 3 RGB, right? They add another channel, use the mark from the segmentation as another channel as the input. And here the training steps. Yeah, you can go over this later on if you are interested. And also they do like flip images. Actually, when we do augmentation, we can do like flip images. But in this case, if I did not do flipping because I think if you flip, then they are not same, right? They are not same. Like if I flip my face, then I'm not the same. So I did not include flip in my, but they do this creatively. They flip, but assign them a different ID. Then they increase their like training data set. Because as I said, well, in this competition, we have limited training data set. So yeah, they got a boost from 0.006. Actually it's a huge. If you look at the difference between the scores of these leaders. Actually, they all use all the top players, they use flip images, so no difference. But well, so this is the structure of their model. I'm not go to detail for that. And in this, they also did super labels. It's like semi-supervised learning. They take some test image. They feel very confident about this image, the prediction on these images. They put the prediction of this test image into the training data set. So it gives 0.001 improvement. Well, we may think it's not worth it, but you see, they are close, their scores. So also they did class balance. Also class balance went, okay, yeah. So class balance also have some boosting. Another thing is here shows how they do the class balance. Second place, they tried a lot of models, and they also do flip, and also pseudo labeling. It's like for the top players, it's quite some standard operation, but for me, it's still quite new. And this second place, they use ensemble. They just assemble all the models that they have and finally push the score. Actually, if you compare single model, they have 0.97. Then if they use ensemble, they got boost in 2002. Oh no, 0.002. And I want to mention the third place. Actually, this third place solution I learned out. I learned out of how they do the selection of third place. Where's the third place? Third place, how they choose their validation set and how they choose their training set. Also, they do flipping, double the ID well. And also, they also this team also uses some more accurate bounding box. The loss function they use is arc phase, cosine, use cosine similarity. Oh, actually, they do make good use of the figures only have the ID will only have one images. Also, they make good use of one ID have a lot of figures. They say the boost if they actually initially the score is about 0.9. Actually, mine is also close to that. But after that, to improvement, the score go up to almost close to 0.97. All right, almost done. So my learning from this competition is first decide how many time I want to plan to put in, and check the what gap between my background and also the requirement of this competition. Then set expectation. Just as from this, I set my expectation is from this competition. I want to try 2 CNN architectures and know the pipelines of face recognition. Yeah, I think I did that. So then during and after competition, I think most important things is after competition, and we need to go back to look at the solutions. Even better if we run the winner's solution, their code, then we can get, we know what improvement we can get. And also read a paper, then know what I'm doing. Otherwise, I maybe get in trouble of like try a different model, then do ensemble, and then fine tune the model. Yeah, but now I lose the big picture. So after reading paper, I got a very long to-do list. Now, I cannot do all this. I just do, hey, what's the easiest to do? Yeah, that's my. Oops. So yeah, last slide. I want to thank this Venture Lab and our hosts and organizers, and also Happy Wheel and many contributors. Yeah, thank you.
Great, thank you so much. Congratulations. 183rd is really good for your first competition. Let's give them another round of applause.
Thank you.